So we're Team 8. We've been working on our RC car drone, and today we're going to talk a little bit about RF communication and some of the general ways that it's done nowadays with Wi-Fi, Bluetooth, and some other architectures. And my name's Jared.
I'm Brandon.
I'm Mike.
I'm Matt.
I'm Marvin.
Alright, so just going through a presentation today, we're going to talk about a few things like the electromagnetic spectrum in general, just a few basics about it, how basically different bandwidths are set up for use. We're going to go into some of the hardware, and Brandon will talk about some of the modulation and demodulation and how that's done for radio communication. We're going to get into the noise and then Bluetooth in particular at the end of the presentation. And RF communication in general, it's basically using electromagnetic waves to transfer information rather than like us talking right now, which is just pressure waves, or using wired communication. And that's one reason why it is so important, is because with wired communication, you have the issue of you have to have physical connections between your two sources that are communicating back and forth. And that has a certain limit with range, really, unless you're willing to spend a large amount of money. So back in the day, like when they were using telegraph lines, we'd have large lines pretty much going across oceans to actually communicate across continent. And then speech-wise, it's just not efficient for power transmission. So we can't actually send out audio signals for miles and miles and miles. So for just even like from one city to another, it's not viable. So it's a way to communicate long distances without having to have a physical link.
So I'm going to talk about the electromagnetic spectrum. Basically, this is just the range of all possible frequencies of electromagnetic radiation. And so what that radiation is it's photon particles traveling like waves through space, which carry radiant energy. It has both electric and magnetic field components that are perpendicular to one another. How we describe these waves as three main physical properties: their frequency, their wavelength, and then the photon energy. So on the side here, I have a graph that just kind of shows the whole electromagnetic spectrum. Theoretically, this is infinite, right? Because the smallest wavelengths can be smaller than the smallest atom, and then the longest wavelength would be the length of the whole universe. So one thing we do to try and break it up is we divide it into different sections. So we have seven different main groups that we split the whole band into. The lowest frequency and longest wavelength would be radio waves. And then as you increase frequency and get shorter wavelengths, you go into the microwave, infrared, visible, ultraviolet, X-ray, and then the highest frequency are the gamma rays. So one way to remember that would be the rabbit's mate and very unusual expensive gardens. So the one we're going to talk about today is in the radio band. So it's the longer wavelengths and the lower frequencies. So the radio band extends from 3 kilohertz typically to about 300 gigahertz. This chart here shows the United States frequency allocations in this range. So as you can see, there's a lot going on to it. Just for reference, this long blue band here is for broadcasting. It's the AM radio frequencies. There's like FM radio, TV channels there. Other different products that take up other bands are like maritime, space research, radio navigation. And the government regulates all this. I know you saw in the last presentation that it's regulated by the government, so you can get fined if you have a product that uses one of these frequencies without getting in touch with them. Okay. So on this slide, I have some products listed that use the radio band frequencies. So for example, garage door openers typically operate around 40 megahertz, baby monitors 49 megahertz, cell phones can be anywhere from 824 to 849. The one we're going to be using for our project is actually the ISM band, which is Industrial, Scientific, and Medical Radio Band. It's from 2400 to 2480 megahertz. So this ISM band, it's a group of radio bands that are reserved internationally for the use of RF energy for, like I said, industrial, scientific, medical purposes that's other than telecommunications. So one main application is Bluetooth. They operate in the range from 2.402 to 2.480 gigahertz. They use a technique called spread spectrum frequency hopping. So what this does is when two devices pair together, we're going to talk about this Bluetooth a little bit later, but what this does is when two devices pair together, they jump between 79 individual randomly chosen frequencies. So they transmit the transmitters change frequencies 1,600 times every second. So they're going together, bouncing around, and that way you don't have any interference coming from other devices. And even if you do have one, it's such a short time that you barely see any effect of that.
Okay, so to create and manipulate the signals that Matt was talking about, you need hardware. And there are different types of hardware. You have ones to transmit signals, and that's a transmitter. You have the other end, which is receiving it, and that's a receiver. And there are other components within these, and they're amplifiers, modulators, oscillators. Transmitter, like I mentioned, is going to transmit a signal. It consists of a power supply. Then you have an RF oscillator that creates the carrier wave oscillation signal. A modulator will add information to that carrier wave. The power amplifier will amplify the signal and then send that out to the antenna that will convert it into electromagnetic waves. All right, so just some quick design principles for an RF oscillator. Like I mentioned, it converts a DC to, you have the active component here that's biased, and it converts that DC to the RF signal, the carrier wave signal that you want. They utilize strip line technology, so if any of you take an EC 405, you use the microstrips, and that's because as you go higher in frequency, you have a smaller wavelength, and it's a lot smaller than the lumped elements like a capacitor or inductor, and you'll get a lot of reflections, and that causes interference. And the way you design is you get a package, transistor, diode, whatever you want. You find the S parameters at a desired frequency. You determine the stability there. From the stability, you get a stability circle that you would plot on a Smith chart. And from that, you select your gamma in that's in the unstable region. And from that gamma in that you chose, you can get gamma out because they're related. You can also get gamma S. And commonly, this is the common equation you use to create an RF oscillator at high frequencies. So it's just, this is where they get the term negative resistance. Next I'm going to talk about antennas. They're matched to a transmitter receiver, and they have to be matched properly so they can deliver the maximum power. Like I mentioned previously, they convert this electrical signal into electromagnetic waves that travel through space. The radiation pattern is an important characteristic of an antenna. When you're looking at a radiation pattern, you're looking at the far field pattern, and it can either be omnidirectional or directional. And the omnidirectional pattern, basically, you'd see this theta right here, it'd be almost a donut shape. The directional is obviously pointing in a certain direction. This is how you would measure the gain of antenna. You first want the directivity, and that's the power density in a certain direction versus or over the antenna power density of an isotropic antenna, which is an antenna that just radiates in all directions, doesn't exist in nature. Then you have your antenna efficiency, and you increase the efficiency by matching properly. And the gain is just the efficiency times the directivity. And the quality factor is just the Q factor that determines how sharp your signal is. And it's important to note that higher quality factor, the input impedance is more sensitive to changes in frequency.
So you can't really talk about RF communication without talking about modulation. As Jared mentioned earlier, you want to take something such as a speech signal and transmit that. In order to do that is modulation. So basically it's the process that maps a low frequency signal to a very high frequency signal based on properties of a periodic waveform such as amplitude, frequency, and phase. And that carrier frequency, that modulated signal, is what we call carrier communication. So starting with amplitude modulation, you may have heard of that in your car, and it was very popular back in the day. And really that was because you could transmit these speech signals over long distances. And it has a relatively simple transmitter and receiver. However, it's power inefficient, and it's very susceptible to noise just because of all the noises embedded in the amplitude of the signal. So once frequency modulation came along, it kind of took over just because of the fact that it's not as susceptible to noise, thereby making a better sound quality. And frequency modulation works just by varying the frequency component of the signal. So this is one of the most common methods that we use now, especially for radio. That's why you have your AM and FM in your car today. But it sacrifices since we have better sound quality, we have to give a larger bandwidth, and it's impacted by physical barriers. So phase modulation is really related to frequency modulation by a integral and derivative relationship. They're really inseparable. Jump discontinuities cause the phase to change instantaneously, causing ambiguities to rise in demodulation. So that could be a problem if you don't limit your phase. And I bring up frequency shift keying, and phase shift keying is essentially a digital modulation scheme to convey data. And phase modulation really has complex receiving hardware, so you don't see it in your car, really. So here's some pros and cons to AM and FM. As I mentioned, AM is poor power efficiency, has lower quality, and is very susceptible to noise, but its bandwidth is very low, which is good, and it's relatively simple in comparison with FM, where it's a little more complex. It has a higher bandwidth, but we do get that power efficiency, we do get higher quality, and we eliminate the noise. So demodulation is the recovering that transmitted signal. We have the signal, and what we do for AM is a envelope detector, which basically envelopes the modulated signal in order to recover that original signal. So this is also known, demodulation is also known as detection as well. So you may hear the envelope detector if you think demodulation. And because of the low cost and superior performance, FM can use phase lock loops. So here's a little demonstration of amplitude and frequency modulation. So we have a signal. And it's a little harder to hear, but it's just at a constant pitch. And this is amplitude modulation based on the different frequencies. And then if we switch to frequency modulation, the frequency is changing rather than the amplitude of it.
And you may have heard Brandon mention several times that noise is one of the largest issues that you consider when you're talking about how you're going to modulate your signal. And noise in general is just kind of the random changes in an electrical signal. It has a number of sources. It can be from issues in your channel, so whether something else is going around in the air, or just things in your circuitry that can actually create noise. So issues with the channel is obviously for longer range communication, the further you're transmitting something in the channel, the more susceptible it is to a larger range of noise. And it's dependent on several factors. So just weather conditions, buildup of charge in the air. If there's a storm going on, that can create some electromagnetic noise just from that. And then any electronic device is going to create some amount of noise because, as we all know, flowing current produces electromagnetic fields. So especially high current devices like motors and things can generate a fair amount of noise. So that's one reason why this building in particular is very noisy. But sorry, you're a little
Yeah.
And then even just beyond noise a little bit, you have other interference issues. So other broadcasts are going to interfere with your signal as well. And even your own signal can kind of interfere with itself. So when you're, like for instance, if you're transmitting from one tower to another, obviously your signal is going to take the direct path, but because we don't have 100% amazing directive antennas, it's also going to scatter in all other directions, and some of that signal might go into the upper atmosphere and reflect off a rain cloud, and it's going to also come down, and there's going to be a slight time delay between the arrival of the signal on the direct path and then a delayed version of the signal. So you have this time dispersion, which is also another factor that you have to consider when you're doing modulation and demodulation. And then beyond the actual channel and what's going on in the air, there's also your circuitry as well. So there's a number of factors that can create noise in your circuitry. So you have more complex things like shot noise, which is created just by the fact that we have a discrete number of charge carriers. So even if you think that you're having a constant current flowing, the electrons themselves are still arriving discretely, so one at a time. It just has small, discrete jumps of charge creating some noise. And then you also have more relatable things like thermal noise. So that's also the just random motion of electrons due to heat energy. And that tends to go up with larger amounts of heat, obviously, and also larger resistor values. So one thing that we try to do is limit resistor values in our circuitry, just because larger resistors will produce more noise. And then on that note, bandwidth as well is important, because if you have a larger bandwidth, you're going to capture more noise, since noise is, for the most part, even across all frequency ranges. So you're going to get a larger capture of noise if you have a very large bandwidth. Wherever you're honing down and you have a very tight filter, you're only going to get a small amount of noise in there. So there's a few methods for reducing noise. Just for simplicity's sake, if we just have like a simple inverting amplifier, just choosing the actual resistor values is one way that we can do that. So if we wanted a gain of 10, we could have resistor values of, say, 1,000 and 100, which would be better than picking something like a mega ohm and 100 kilo ohms, just because there's going to be more noise generated just from the largest of those resistors. Another thing we can do is band limit our circuit. So if we were using this circuit just to amplify, say, an audio signal, we wouldn't actually need to amplify it for all frequencies. We'd be just limited to the audio range. So one way of doing that would be just to add a simple capacitor across the feedback loop. So we could essentially make that act as a low-pass filter. So we're only actually passing the low-frequency signal, which is where our desired signal is going to be. So we're not amplifying all of that high-frequency noise as well, which is going to help reduce some of the noise in the output.
All right, now I'm going to wrap things up by talking about Bluetooth a little bit. So what Bluetooth is a radio frequency technology that operates on the master-slave communication principle. Basically what this means is that there's like a centralized primary device that manages communications to a number of secondary devices in the network. So some of the benefits of using Bluetooth technology is that it has very low power consumption compared to some of the alternative wireless solutions, and that it's self-contained. Anyone who's used Bluetooth understands that it pretty much sets itself up with a push of a button. So Bluetooth contains both the physical RF technology and the protocols to set up the network. So if you're trying to set up two computers over Wi-Fi, it's a lot different to have to deal with IP addresses and ports and sockets and all that. So Bluetooth basically does it all. And another benefit is that it can support multiple applications without having to configure too much. So the first step in setting up a Bluetooth network is to pair some of the devices. So you put the devices into pairing mode, which uses service discovery protocol, and this is actually the only time where all devices can see each other on the network. So they'll be able to communicate and pass various parameters and their IDs so that every device on the network knows what each other device is capable of. So in this type of network, up to 7 devices can be connected to one central master device. And as Matt mentioned earlier, Bluetooth uses the frequency hopping spread spectrum. And basically what this does is it switches the frequency that it's broadcasting at several times a second. And the way that Bluetooth handles this is the master chooses a pseudo-random sequence, and it sends that to all the other devices so they all know which frequency is the current one that's being broadcasted and which one's the next one. So the communication pattern that it follows is that the master will transmit on one time slot, and then the consecutive time slot will have the slaves transmitting. So it alternates back and forth, and the pattern is known so that you can minimize the noise and interference with other Bluetooth networks or anything else that's in the 2.4 gigahertz band. So for Bluetooth, there are 2 main types of connections. You have the synchronous connection oriented link, and what that is a symmetric point-to-point link used for voice communication. So when you're having a phone call, you want equal amounts of data going and coming. So it allocates the bit rate symmetrically. The other type of link is the asynchronous connectionless, and this is used for all data transmission. That's what they use when they're pairing. That's how they send the IDs, the parameters, and stuff like the packet headers, or just overall status of the network. Like if one of the secondary devices is going to drop out, it sends that data through ACL. So a very attractive side of Bluetooth is that it supports multiple applications. Anyone who's used Bluetooth understands that there's different types of things that you can do with it. It's not just the headsets that they used to be. So every device comes pre-built with a set of applications that they call profiles, and there's more than 30 that are managed by the Bluetooth Special Interest Group, so they're all very standardized. Any packet or any device that says it can, say, operate as a headset, we'll be able to do that, and we'll be able to set it up, and it'll work very seamlessly. So some of the applications that we can do are file transfer, audio streaming, you can connect to a fax machine. There's a wide variety of them. So does anyone have any questions about anything?
You threw an AM and FM demo into an online simulation.
Well, it's just better to do it ourselves. So we just set that up in the lab.
I mean, continuing from there, it'd be pretty fun.
What was that?
It'd be pretty fun to do it online.
Oh yeah, I'm not going to develop that app though. So.
Any other questions?
Do you guys have any challenges with potential RF interference with your particular project when people are in your project sense with the RF communications?
So for our project, we're not really going to have any issue with the Bluetooth communication, because one thing that is an issue with Bluetooth is it does have a fairly limited range. But for our application, the phone that's actually going to be controlling our RC card is going to be directly on the card itself. So it's not going to have any issue with signal strength or anything, and it'll be the strongest signal being received by our Bluetooth receiver on our board. So we shouldn't have an issue really with any interference.
If we drive it around any microwave ovens, we might get into something like that. But like we said, it changes 1,600 times every second, so we'll get this really quick. And Bluetooth actually has algorithms that are meant to kind of counter that, get rid of the noise you'd see. So.